Lecture 20 is mostly about Kirchhoff rule, and this is what we talked about last time already. So I will talk about the other rule that we didn't cover last time, and in the process also reviewing what we did in the last lecture. Okay, so this well, the rule that we haven't talked about is what we call the current rule. And basically what it says, so current rule is called a current rule. It's one of the two Kirchhoff rule. The one that we covered last time is called the loop rule, or the voltage rule. We're gonna review that in a moment. But this is the new one. It's called the current rule. What it says is that at any junction, the total current in will be equal to the total current out. Okay, and it's easier if we just demonstrate this one. So consider a situation like this. So you have two resistors connected in parallel. Parallel means one is connected like this and the other one is connected like this. Okay, and let's call it R1 and R2. And then we connect this circuit to a battery like this. Okay, and let's just say the battery is given by some voltage, let's say V0, and it might be 12 volt or 10 volts or 9 volts, doesn't really matter here. But this is different from what we talked about last time, for one obvious reason. So last time we talked about like starting from one point in the circuit and then go around to complete what we call a loop like this. And you can see now that there are two possible loops that you can go. Okay, so this is different. The current rule that we talk about at this moment is about any junction that you have in the circuit. So a junction is just like intersection in a road when you drive. So in this case, there are two junctions, one here and the other one here. Okay, so these are junctions. So junctions require at least three branches. Okay, if you have just two branch, those are not junction. Okay, so this is what we have here. So let's consider the junction here. So this rule essentially says that for this junction, any current flowing into this junction will be equal to the current flowing out of the junction. So what this means is that if you write current flowing this way to be, let's say, I1, so current labeled by this I1, and then you say this current I2 is flowing out from the junction, and then you say the third one, let's say I call it I3 like this. Okay, so the current rule says that flowing into the junction must be equal to flowing out of the junction. Well, flowing into the junction is I1, right? So I into the junction, I in is just I1, and then I out from the junction, there are two of them, which is I2 and I3. So we just say I2 plus I3 like this. Okay, and the rule says I in must be equal to I out. So that means I1 must be equal to I2 plus I3. Okay, so for some of you, this might be totally, like natural or intuitive. But for those of you who are wondering like why this should be the case, it actually stems from the fact that you cannot have, concentration of charge anywhere. So it means that for any junction, you cannot have just current flowing in without flowing out. So if you remember last semester when you study fluid, um, you know, the movement of fluid, there's one thing which is called the equation of continuity. And it's also based on the very same fact that you cannot have fluid, concentrating at a certain point, meaning that you cannot have just water flowing into some region without flowing out, because otherwise, where does the the water gonna go? It's the same thing here. Charge cannot just disappear or cannot, like appear out of nowhere. So you cannot have, things just flowing in without flowing out, or things just flowing out without any incoming charges, right? So this is kind of, again, like the continuity equation for charges in the circuit, right? So we have I1 equal to I2 plus I3. So the significance of this is that in this kind of circuit, usually you will be solving for, the unknown current. And by the look of it, it might look like there are three unknowns, I1, I2, and I3. But because of this Kirchhoff rule, the current rule, I3 is not independent of I1 and I2. So using this, you can write I3 simply equal to I1 minus I2. Okay, so you don't have the third independent variable. It's actually a function of the two variables I1 and I2. So you only have two free variables that you need to solve, not three. Okay, not three. So only I1 and I2, because I3 is a function of I1 and I2 like this. Okay, so this is gonna make solving the circuit a little bit easier, because you don't have too many, variables. And once you have this, then you can apply the rule that we did last time, the other rule of Kirchhoff rule, which is the loop rule. So the current rule and the loop rule, in total, makes Kirchhoff rule complete. So you're gonna use two, injunction. So now we're gonna apply the loop rule. So how do we do that? Well, now that the current is written, so we can pick some point in the circuit and then we start walking around the circuit. So the first point, well, not the first point, well, the point that I'm gonna pick is this one here at the corner. Like usually it doesn't really matter which point you pick, but this is kind of like my kind of habit of picking the point right after the battery here, so that the battery gonna be the last, element in the circuit that I encounter when I'm about to complete the loop. So there are two possible loops. The first one is the one that goes like this, which I will call loop number 1. And the other one is loop number 2, which is going the outer loop, like this. Loop number 2. Okay? So, well, you might argue that, hey, there's the third one, because you can start inside this loop and then go around this. You can do that, but that's not gonna, give you any new information, because there are two unknowns, I1 and I2. So if you choose wisely, then you only need two loops to write down the equation. Because remember, the number of equations and the number of unknowns should be the same. Right? So if you have too many equations, then you are kind of like, you're gonna have some, repeat of information somewhere. So you don't need that. So I only need two loops in this case, number one and number two. So let's start with number one, which is the purple one. So it's what we talked about last time. So you start here, and then you start walking along the route that you decided. So walking along this does not give anything because there's no resistor there. And now you start to turn right at the junction here, right? So when you turn right, the current passing through R2 is I1 minus I2. And remember that if you're going along the same direction as the current, which what we have here, then it's the minus sign. Okay, so I'm gonna have the first term to be the minus sign times IR, right? But my I is I1 minus I2 times the resistance R2, like this. And then I reach this junction and then I turn right. And then I go across the battery. And I go across the battery from minus to plus. So I'm gonna have plus V0. And then I reach my starting point. So I have completed the loop and I set it to 0 like this. So that's it for loop number one. Let's do loop number two. So loop number two, you start at the same point, but now you don't turn right at the first junction, you go straight. Okay, so when you walk here, the current is I1, but when you go across the junction, my setup is to call it I2, okay? Because there's no reason I1 has to be equal to I2. So it's gonna be I2 going across R1. So my first term is gonna be minus, right? It's minus sign because we are going along the same direction as the current. So minus I2 times R1, that's going across that resistor, and then going around the loop and then encountering the battery again. So that's going to be plus V0 equal to 0 like this. Okay, so that's going to be the other loop. So these two equations give you all you need to solve for I1 and I2. Okay, so we're going to do that. So let's solve for I2 here so that we can plug into the purple equation. So I2 is simply V0 divided by R1. Okay, so the first equation becomes, minus I1 minus I2. I2 is V0 divided by R1 times R2 plus V0 equal to 0 like this. And then we want to solve for I1. Okay, and when you solve for I1, you will see that I1 is going to be equal to V0 divided by R1 plus V0 divided by R2. Okay, so it's just algebra, so I probably don't need to do any more details than this. Okay, so this is I1, which is this one. So we have solved for everything that we want to know. So let me redraw this in a little bit cleaner diagram. So we have two resistors, and then we have a battery here, V0, and then R2, and then R1. Right. So we know from our calculation here that I1, which is current passing through this branch, is equal to this one. Okay, so maybe it's better if I use the same color here. I1 like this. Okay, so one thing that we can do is that we are always interested in what we call the equivalent resistance. So meaning that what resistor I need to use to be able to reproduce this circuit such that it gives the same current. So I want to replace the whole resistors by a single one, R total, such that the current flowing through the circuit is the same as I1 that we have here. Right. And well, that's kind of easy because you just pick R total such that it gives the same I1. So what we mean is that I want V0 divided by R total. Right, so that's by definition that's I1 in this circuit equal to I1 in the other circuit, which is V0 divided by R1 plus V0 divided by R2. And you can see that the battery voltage cancel out, which is good because, I mean, if you want to find the total equivalent resistance, it shouldn't depend on what battery you use. Okay, so this is how you get this formula for adding parallel resistors. Is 1 over R total equal to 1 over R1 plus 1 over R2, like this. Okay, so in a sense, we are kind of, deriving this formula with using Kirchhoff rule, and this is good because I think a lot of you know that this is the formula for adding parallel resistors. Okay, but you can kind of like, you don't have to go through Kirchhoff rule to actually get this formula, because you can just say, okay, if you connect the battery to R1 and R2 like this, the voltage across R1 and R2 it has to be the same because it's set by the battery. Okay, and you can use that fact to actually derive this, and you're gonna get the same answer. All right. So at this point, we actually, have the two important formulas for combining resistor, and you're gonna be using this quite, a few times. So for those of you who are not familiar with this, it's probably a good time to, like look at this and then see how you can apply this to various situations. But before that, let's summarize a little bit. So if you have series resistors, series R, and you don't need to limit yourself to just two. If you have like multiple of them, R1, R2, R3, R4, but they have to be in series. Okay, all of them has to be in series. So this is equivalent to having a single resistors, R total, where R total is equal to R1 plus R2 plus R3 plus R4. And then if you have R5, R6, R7, you just keep on adding. All right. So combining resistors is probably most useful if you want to find, like the total current flowing in the circuit. We're going to look at the example in a few moments. But, this is the formula that you probably need to remember. And then the other one we just talked about, which is parallel. And that's when, well, they're in parallel. And again, you don't have to limit yourself to just 3. Any number of resistor in parallel, then you can write the formula to be 1 over R total equal to 1 over R1 plus 1 over R2 plus 1 over R3, like this. And then if you have combination of series and parallel, you just try to group the smallest, group together and then try to, work your way out. So let's look at some example. So let's consider a circuit that contains 3 resistors, one here and 2 in parallel like this, and they are connected to a battery like this. Okay, and let's say this is R1, which is equal to 10 ohms, and this is R2, which is 20 ohms, and this is R3, which is 40 ohms. And then the battery is 12 volt. So V0 is 12 volt. And this is kind of, a classic problem in this kind of circuit analysis. And there are many things that you can ask in this problem, like what is the total current, what's the current through R1, what's the current through R2, R3, like that. Okay, so it makes a really good practice for, like mastering this kind of problems. So the first thing we're going to ask is, what is the total current flowing in the circuit like this? So the total current is always the branch that is right after the battery. Okay, it's not this one, but it's the total one, because afterward, who knows how you're going to have the circuit, the current flow, along, into different branches. But in this case, the total current is the one that's flowing out from the battery. So it's this circuit, it's current here that we are interested in. Okay, you can use like Kirchhoff rule to write the equation for like this loop and then this loop or something like that. But if you have easier way to solve the problem, then that's probably the way to go. Okay, so the way to do is that we want to try to combine resistor to reduce it to a single one. Okay, so in this case we have 3 resistors. We will try to reduce them. So let's draw it like this. So this is 10, 20, and then 40 ohms like this. So you look at this and then you ask yourself, what is the smallest unit of resistor in this circuit? And the way to do is that you want to combine the same kind of connection. So series, all series, and if it's parallel, then it's all parallel. You cannot have a mixture of them. So in this case, the first thing that you can do is to combine these two together, which are in parallel. So I can write something like this. So the red one is the combination of these two. So these two becomes this. And the 10 ohms on the left hand side, we didn't touch it, so there's no change. So if you combine 20 and 40 in parallel, what is this resistance? Well, that's when you do 1 over R equal to 1 over 20 plus 1 over 40. Okay, and just to make it clear, let's call this R4. Well, R4 is not something in the circuit, but it's what we write as the combination of R2 and R3. So 1 over R4 equal to 1 over 20 ohms plus 1 over 40 ohms. And this will give you R4 equal to about 13.3 ohms. Okay, so solving this can be tricky sometimes. So you have to be careful about like finding the reciprocal of the fractions. But just take your time to solve for this. Anyway, so now that we have R4, we can then combine these two together, right? Because now they are in series, so just combine these two together, and this is easy because you just add them. So we have R total equal to 10 plus 13.33, and that's going to be 23.33 ohms. So that means from the point of view of the battery, everything will look the same if you replace the 3 resistor with a single one. So this one gives the same total current as the circuit shown here. So that's going to be 23.33 ohms, and the voltage is 12 volts like what we have before. And the current I here, let's call it I1. So I1 is simply voltage divided by R total. So that's going to be 12 divided by 23.33. So that's going to be about 0.515 amps. So that's the total current flowing in the circuit. Okay, so we can write 0.515 amps here. So that's going to be the current flowing out of the battery. We move up here. So we can stop here, but we can ask also a few more questions. For example, we might be interested in where exactly do you want to look at? Is this the previous page, or is this page? Previous page, like this one. All right. So the other thing that we want to know is also what's the current flowing in these 2 branches. So we can write I2 and I3 like this. Okay. And one thing that we know from Kirchhoff rule is that the current flowing into this junction must be equal to the current out from this junction. So from this, it should be clear to you that I1 must be equal to I2 plus I3. So essentially what it means is that we have the total current to be about 0.515 amps. It has to split itself to I2, and the remaining current will be I3. Okay, so if you know what is I2, then I3 is easy because you just subtract I2 from I1, and then you get I3. Okay, so we want to figure out what is I2 and I3. And let me point out that you don't need to have the same current as I1, as I2 and I3, right? So they are split in the, like, they don't have to split equally because the resistance are not the same. Okay, so then, so what to do? Well, we can calculate the voltage across R2 and R3. But the problem is that we don't know I2 and I3. So what can we do? Well, the thing is that we know the voltage across R1. So let's call it V1. Like this. So how do we know V1? Well, because we know R1 and we know the current flowing through R1. So V1 is simply I1 times R1. And both something that we know. So let's just do that. So let's just write 0.515 amps for I1 and then R1 is 10 ohms. So V1 is 5.15 volt. So that's something that we know. Okay, and if you now remember the Kirchhoff loop rule, if you go across, right, the voltage that you get from all the resistor must be equal to the voltage of the battery. So if V1 is 5.15, then the rest has to be V2. So V2 like this. Okay. So what I mean is that V1 plus V2 must be equal to 12. And you can argue that for that to be the case if you use Kirchhoff rule, or you can just, you know, well, I think it's probably most rigorous if you use Kirchhoff loop rule to you know, like argue that. But in any case, V1 plus V2 must be equal to 12. And we already know V1 to be 5.15. So V2 can be easily calculated. So V2 is simply 12 minus 5.15 volt. And that's going to be 6.85 volt. So that's going to be the voltage across R2 and also the voltage across R3. Right. So let me kind of redraw the circuit a little bit because it's getting kind of crowded. So R1 here, R2 here, and R3 here. Okay, so we have R1. I'll just write the number for the resistance, so 20 and 40, right? So again, we know that V1 is 5.15 volt, and then we know V2, which is 6.85. And again, we know because V1 plus V2 has to be equal to 12 volt here. Okay, but if we know V2, then we can calculate I passing through R2 because it's just V equal to IR. Right? So if we call this to be I2 and we call this to be I3, then V2 is equal to I2 times R2, right? Ohm's law. So I2 is simply V2, which is 6.85 divided by R2, which is 20. So I2 is 0.3425 amps or something like this. And now there are two ways to calculate I3. So you can say I3 must be I1 minus I2. So 0.515 minus 0.3425 amps. And that gives you about 0.1713. Right? So it might be some rounding, you know, error, but we don't need to be super precise. Okay, so you can calculate I3 like this. Or if you want to double check, you can also say V2, which is also the voltage across R3. So it must also satisfy Ohm's law. So it's going to be I3 times R3. So I3 must be 6.85 divided by 40. And you're going to see that it gives the same answer as the other way of calculating. Okay, so this is good, and this is something that you should be doing in this kind of problem, is to double check whether it's, you know, consistent within, you know, like the whole, you know, circuit. Like if you use different way of calculating, for example, you calculate the current like this, and you calculate the current like this, and if they give the same answer, then you can be pretty sure that you did nothing wrong. But if they give different answer, then you have to double check again. Okay. So another thing that you might get asked is that, okay, once you know the current for each resistor, and you might want to find the power of each one. You know, the power means the power loss in each resistor. Then you just need to calculate P equal to V times I for each resistor. For example, this one, what is the power loss in R1? So P1 will be just V across R1, which is V1, times I across R1, which is I1. So that's going to be simply 5.15 volt times the current, which is 0.515 amps. Right, and then if you calculate this, then you're going to get 2.65 watts. Okay, so that's going to be the power loss for this resistor R1. And you can also check, so I'll leave this for you to check by yourself. You can re-express this one using Ohm's law. So it can be V squared over R1 or equal to I squared times R1 like this. And you're going to see that you get the same answer no matter what formula you use. And then you can do the same thing for R2, right, to see what's the power loss for R2, and then you can do for R3, and then you can calculate what's the power loss for R3. Okay, so I'm gonna write down the answer, and just make sure that you know how to calculate. So P2, which is the power loss in R2, that's gonna be 2.35 watts. And then P3, which is the power loss in R3, that's gonna be 1.18 watts. Okay, so just make sure that you get the same answer that I did here. All right. So I'm gonna take a break now because the remaining thing for the lecture is RC circuit, which is gonna take some time, and I don't want to interrupt our discussion. Okay, so I will take a 10-minute break here, and I will see you soon. All right, so see you in 10 minutes.